All right, Anton, the floor is yours.
All right. Um, are you seeing the presentation?
Yes.
Yeah, we see a GitHub.
What? Yeah,
Like
right,
a,
right.
yeah.
It's a screenshot. It's not
Nice.
the GitHub. Yeah, I wasn't sure about the format, so I've made a little presentation just to give this talk like a more structure. If everyone is okay with that, I guess we'll start. So the story began with big chain DB guys creating an issue on GitHub saying that Tendermint shows time-dependent performance degradation, which means basically that each time Tendermint, it takes longer for Tendermint to create a block for some reason. And within a few days, we confirmed that. A part of this was due to the issue in TM bench, which we later fixed, and also mempool rechecking transactions. So after Tendermint commits a block, it rechecks all the pending transactions which are left in the mempool to see if they became invalid. Yeah, and we used to have a very big mempool. So what was happening is with every block, you kind of also need to recheck all the pending transactions, and this like adds some amount of time. So what we did is we fixed TM bench and we also limited the mempool, but the core issue did not disappear. Although the curve was not so steep, there was still like this performance degradation.
Can you tell us what we're looking at on that graph?
On this graph?
Yep.
I think it should be the amount of transactions or something like that. I don't remember actually. Yeah, I think it's a number of transactions per block given constant load, like say I don't know, 5,000 transactions per second or 10,000 or something like that.
And the colors?
The red is probably standard deviation, and I forgot what yellow is. But the blue one is the most important. Yeah, so after a few more hours, I found out that the time to index a block can be quite high, and by quite high I mean 23 seconds. So
Nice.
for those who are not aware, we have this indexer, very simple indexer, which takes a block, takes transactions, and creates like a key value pair for each transaction with a tag, which can be like a hash, for example, a hash of transaction, and the result. So people later can query a transaction result by hash. using the RPC. And it can also index tags from deliver tags response. It's very simple. It also uses Go leveldb database. And I did a profile. I profiled this piece of code, and you can see that I'm in this particular example that compaction takes 10 seconds. In Go leveldb, compact transact, stable compaction builder run, something like that. If you ask me like why it is happening, I don't know. I'm not a database expert, unfortunately. I do have some thoughts of why this is happening. I don't know if all of you know what LSM tree is, log structured merge tree. Do I need to explain what it is?
Maybe quickly glance over it. Just give a quick rundown what the properties are, and then so we
okay
know the definition.
Yeah, so the very basic overview is like before we in computer science, like the guys like first they invented trees, and like B trees, B plus trees, red black trees, and in almost all databases they use B plus trees for indexes. Then later a guy, I forgot his name, but he came up with the idea of why don't we have not just one tree, but like a series of trees or some structures where every like the next structure is a bit smaller. So the thing at the at the top can be the smallest tree, and it fits like in memory, or even in this it can be very cache friendly. So like processors right now have cache lines and L1, L2, L3 caches. So we have a few trees, and it goes like this. Like the write comes in, it goes to the memory, it goes to this tree, like small tree, and when this tree in memory fills up, it goes to the log, like and when this log, it's actually in implementation detail, but it goes to the second tree, and then that's how it like propagates, and you can configure the number of levels. Like it can be just like 2 trees, like here we have like C0 and C1, like a small tree and a big tree, and small tree can be in memory and big tree can be on disk. Yeah, this is basically it. And this is like a very basic overview. It can be implemented as a series of, as a series of SS tables. Like, as I said, the write comes in and goes to the memory, then it goes to the log file on disk, small log file. Then when this SS table, like very small, gets filled in, the write it will like it will be merged to the bigger SS table, and this process called compaction. Basically, when we flush writes from the top level to the bottom levels, this process is called compaction. And my theory behind the Go leveldb bug is that for some reason, I don't know, I don't actually have a theory, but the number, it's obvious that the number of the size of the tree is growing, and even if the number of levels stays the same, for some reason it just takes longer each time to do a full compaction, because C leveldb does not have this bug, or with C leveldb it takes a like compaction have a predictable time.
So the assumption is that the implementation we use has some shortcoming or fault that leaks or makes it grow over time.
Yes, yes. And I created an issue in the Go leveldb repo on GitHub. Nobody responded so far. That's a very well supported project. Good support. Yeah, and I kind of punted on this issue for a while, just to give guys the time to respond or something.
Well placed.
Yeah.
So you
and we also have this. Sorry, what?
So you tried it with C leveldb and the issue's not there. We don't get the slowdown.
Right. Yeah.
What if we turn off indexing?
If we turn off indexing, the issue goes away because there is no indexing.
But we're still. Have you tried that? I just want to make sure that we're pinning it down correctly to indexing. The profiling seems to suggest it's coming from the indexing, but have we tested turning it off? And because we'd still be saving blocks with lots of transactions even without indexing them.
Yeah. Yes. I don't remember exactly. I'm more or less sure that I tried to disable indexing, but maybe I haven't run the test suite for good enough time to notice the difference.
Okay.
So I'll do that again, just
okay,
to
thanks.
sure. That's actually a very good point. Yeah, we do save blocks in another place. But there we this is the thing. There we don't create so many records or key value pairs. There is just like one big write.
Right. Well, there's a couple because we save for Like we saved the block meta and the block itself and the commit, I think all.
Yeah, but
separate keys.
it doesn't matter because when you do indexing, you create like 10,000
index.
pairs
Yeah, exactly. Yeah.
per second or something.
Yeah, for sure. So the LSMs are supposed to be, they're supposed to be good for this kind of use case where you're doing lots of random writes, right?
Right, but the interesting thing is that I did a round of benchmarks, and the picture I've got is the B-bolt kicked S, B-bolt, which is B plus 3. It kicked S up to a point of maybe 5,000 slash 10,000 random writes. So like up to this point, yeah, you can see it here. Up to this point, B-bolt is like the fastest thing. And when you hit, I know, 2.5 megs, leveldb starts winning. Yeah.
Interesting.
Interestingly enough, Badger doesn't go that well. I will do it, or maybe some of you can do another round just to like.
Is this on your MacBook, or where is this happening?
It's on my MacBook inside the virtual machine. I should probably do another round like on DigitalOcean just to make sure.
Your MacBook has an SSD.
This is only indexing. It probably makes sense to, I don't know, benchmark reads. But I'm pretty sure that B plus 3 will kick ass again, because B plus 3 are very good with reads, and it's very, very good with sequential reads because it's just one file. So you don't have to go through all the levels in order to,
Could you quickly reiterate what kind of workload we need to optimize for? Is it read heavy? Is it sequential reads? Is it random reads? Like what do we need to optimize for?
Yeah.
With our workload.
As for indexing, we need to optimize for up to for how many transactions per second we're gonna support. That's probably like up to 10,000. And we also need a very good sequential read performance, because as I said, we exposed this /tx RPC where you can fetch the individual transaction, but we also exposed text search endpoint, which uses this text to do which does like this sequential scanning of the index and fetches only like when you need transactions which belong to like a particular account, like Bob's account. And for that, you most certainly need B plus 3. Like you don't need LSM trees for that. We had, and I think we still have plans to also support PostgreSQL indexer. And yeah, and again, indexes in PostgreSQL are B plus 3. Yeah, I also did a round of this, basically performed the same benchmark, but with sync writes. It means like after every commit, after every write, we do an F thing. And here again, B bolt does a very good job, and I'm not sure why, but yeah, it's very performant on the small number of writes again, up to 1,000.
Does it use a different data structure, or how is it different from leveldb and Badger?
Yeah, so C leveldb, Go leveldb, and Badger are all LS log structured merge trees. Dbolt is D plus tree, and yeah, D plus tree is basically, yeah. You see, this is the D plus tree, and this is what bolts offer, right?
Right.
So like both approaches have trade-offs. If you require high random write for output, more than 10,000 writes per second, or you need to use spinning disk. I don't know what spinning disk is. Then LSM is probably a good choice.
Is
if your application is read heavy or doing a lot of range scans, then Bolt could be a good choice.
Is your MacBook spinning disk or SSD?
SSDs.
Yeah. So it's interesting, right? Because given this, basically the only thing we're benchmarking here is a high random write throughput. This indexing is mostly indexing by the hash of the transaction, right? So it's mostly random writes, and get
right. Yeah.
And get Bolt is the best performing, at least for lower amounts. I guess at the higher amount, then C leveldb starts to shine, which sort of makes sense as well.
Sort of, yeah. And also leveldb have or not leveldb, Bolt have transactions.
Right.
And leveldb doesn't have transactions. So it's like provides more better guarantee. So, yeah. So the takeaways, or like for indexing, I would seriously consider C plus tree based database. For other stuff, I don't know. It's better again to do like a round of benchmarks and also like learn read write ratio, because so it also helps, and pick a clear winner. And yeah, LSM tree is supposed to be this like new data structure, which are like very popular right now, but surprisingly, B plus trees are still like doing good for some use cases. I still have many questions. Like I still don't know why compaction takes longer. In order to know this, it will probably be required to like read their sources and try to understand what is happening. And
do you think this is worth the effort, given that the current implementation of leveldb we use seems to be outdated and not
like,
up to par?
Outdated
yeah, it seems to be a little bit outdated, but it is used by Go, Ethereum, and many other like popular projects. Is it worth an effort?
Is it possible it's a regression, what we're seeing? Maybe there's an older version that
Have we looked into tuning parameters like compaction and things like that?
What I did is that I went to the Go Ethereum repository and I looked at what settings they use, and so I copied them over. They use most of the default settings except they tune like write buffer size and cache size and one more parameter which I forgot. Yeah, and if you increase, and they also have bloom filters because their bloom filters are good for if you want to increase read efficiency in LSM trees. That it's kind of the like default hack for LSM trees. You just like enable you just have this separate bloom filter. So yeah, if I increased these two parameters and Go leveldb still sometimes it takes like 5 seconds or 10 seconds, but the frequency of the compactions becomes lower.
Wait, so how often are we compacting now?
With tweaked parameters or with default parameters?
With the new parameters. Right. If we were to use those. Place to sleep.
I will need to check. I don't have a graphs at hand, but it looks like maybe 4x or something, like 4x less, or no.
Oh, cool.
Yeah, I also didn't check if Bolt has the same performance decreases, so I'll need to do that. Yeah, the problem, not a problem. The issue with bbolt is that it has like this bucket API where you need to create a bucket and put the key values pairs there. My guess is that for each bucket, Bolt creates a B+3. So this buckets API is essentially for splitting up for improving performance and splitting the size of because if you have just one tree, you only end up with a very, very large tree. But it looks like you still can put all key value pairs in the same bucket.
For the second point, is there a way how we can test this? And in general, like the benchmarks you create, is that portable? Like, can we just take it and put it on a machine and run it there? Like, for example, bring it on a digital ocean instance on a server somewhere. Maybe that would be nice to just have a range of machines and to see if your findings hold true.
Yeah, let's do that. Yeah.
And when you say tree growing, like what was the max size that you tested in terms of what is transactions? I guess amount of transactions or
the size of the tree.
Yeah, because you have the second point, which seems like an open question. So how far do we need to go in order to verify or to get confidence that the performance doesn't decrease with a growing data set?
Like with Go leveldb, you don't even need to go that far. You just like do, I know, 1 minute test and it starts to slow down, or even 30-second test. With dbolt, I don't know. It's also a very good question. We need to test that too. Because eventually it will slow down. Even PostgreSQL, which I think is a state-of-the-art database, it's very good. I have a couple of friends, other people who I know who are like contributors, very, very smart dudes. And even PostgreSQL can do like up to 1 terabyte on one machine. This is like the size of the single table with the index or a few indexes. What I'm trying to say is that obviously there is a limit. I don't know what is the limit. With the index stuff, it will probably be a good strategy to provide PostgreSQL indexer, so people can, I don't know, maybe do some sharding or or something else. It's an open question.
But with that, it would require an external process, right, for the functionality.
Yeah.
Is that something that you would advise generally, to just offload this kind of concern to something that is specialized in such a workload and not try to fit it into the core code base of Tendermint?
For a serious project, probably, yeah.
Yeah, I think that's right. I think the existing indexing functionality has always just kind of been a stopgap, so that developers can get started and they kind of have a full stack implementation available. But obviously, certainly with Go level DB, it's not going to meet performance needs, and there's obviously a serious issue here. With C level DB, it sounds like it's a lot better, but probably still won't meet the needs of a really high throughput system. So that's still just kind of a placeholder until either we implement a way to connect Postgres directly through the indexing, or you stream it out over WebSockets and then index there. So
do we have an understanding of what the cost would be to switch from Go level DB to C level DB? I presume not much, and from level DB implementation to Bolt.
Cost in terms of
engineering time and impact and changes of code base.
The biggest issue with the C level DBs seems to be just the build process. Just if you want to have a deterministic build system, suddenly you've got libraries in the way. So there's that but you can already compile Tendermint with C level DB just with the build flags.
Right.
So we should recommend that to the big chain guys who identified this, that they can compile Tendermint with the C level DB, and then hopefully, as far as we've seen so far, the issue doesn't exist there.
Right. And in terms of API difference between Bolt and level DB, Anton, maybe you have an idea, like what kind of amount of work it would take, and in consequence, if we could even offer different backends for the same functionality.
Yeah, I wrote like a basic skeleton. So I implemented get and set, delete. I didn't implement iterators. So it would probably require, I don't know, a few hours to implement that.
Is there a way where we can just lower the frequency of compactions? Like, say we compact once every 1,000 blocks. Like, can we set the frequency ourselves?
I imagine that's partly determined by how much memory you have, right? Since it's determined by like when it needs to move that C0 tree into C1.
I don't remember. I'll need to check out the setting.
Okay, thanks.
Cool. Well, it sounds like we should maybe see if there's some way we can ping the Go leveldb guys and see if we can get a response to this. Or
I mean, starting off with sharing them with the session, right? That would be a good.
Sure.
start,
Yeah. I mean, there's an open issue from July that Anton opened, but
yeah.
I was curious that I guess no one else has seen this or what. I don't know. But,
there have been commits to the repo, which is kind of interesting.
yeah, it's still active.
Just still haven't responded.
Yeah, it's still active for sure. Okay, cool. Anything else? Any other questions or comments or follow-up?
Yeah, so there are a number of options. You can probably configure or at least tweak the compaction frequency. Like compaction, expand, limit factor, compaction, L0 trigger, compaction source limit factor, compaction table size. Maybe worth investigating.
Cool.
Would it be possible to have a design document laying out how we could abstract the database away in a way that we can swap implementations going forward?
Isn't that the DB interface does?
Is it already there? Is it already general enough to just say could be satisfied by most in-memory key value stores?
I think pretty much. I mean, the database, the interface has the iterators, and so those might be, and also does it have sync in the? Yeah, so it has the iterators and this notion of like being able to write synchronously or not, i.e. with an fsync or not.
Can we talk about this? Because I see this mentioned a lot, right? And
yeah,
this idea of that you have control if it ends up physically on the device.
Yeah,
it's like pretty much it's an illusion in general, right? Because there are so many intermediate layers that can tell you that you sync, but you really didn't, and in the end, it depends on the drive controller. So is that something that we really that is important to us? Is it part of the guarantees we need to build around? Is it something that's like an axiom that we require? What's our stance on synchronous disk operations?
I think so. I mean, I think there's two separate concerns. One is the consensus write-ahead log, and the other is committing the blocks. And my understanding is that there are a few points in the write-ahead log where we want to make sure we actually persisted something to disk, so that basically, because we presume we have validator signers that are going to prevent double signing, we don't want to be in a position where we signed a vote, crashed, didn't get it to disk, and can't sign it again, kind of thing. So we want to make sure that we persist these things to disk.
Is that to prevent double signing?
it's assuming that we're preventing double signing. I guess actually it's still possible that we could, because if you sign and your device won't let you sign again, but then you crash and you didn't save it to disk in time, there's nothing you can do anyways. So that's something that might need some more thought, because then we could get into a situation where if all the nodes crashed in the same way at the same time, then the network would be stuck because none of their signers would be able to re-sign and none of them would know what the last vote was. But we do, so we protect this by making sure that the, like right now, the signer that we use, like the on-disk file signer, that's right, that thing saves the last signature. So that way, if we fail to write to disk, we have kind of in the write-ahead log for the consensus, at least the signer itself knows what the last signature is, so it can still return it. In the write-ahead log, I think it's important for consistency of the state machine that it actually writes to disk, so it knows exactly where it is. But with more thought and design, it's possible we could alleviate that, but it's kind of a hairy place. And then I think after we commit blocks, we want to make sure that the block, that like everything we've written finally actually makes it to disk. Only kind of once at the end of the block, everything that's kind of in the buffer or whatever should actually get written. No, because otherwise we can recover just by like replaying the block.
Right.
We want to know when we say a block is committed that everything about that block has been committed and synced to disk, and there's no going back.
Right, but it's an interesting constraint to put on something as fragile as a single device, right? Like assuming that this is our reliability guarantee for example, for a non-double signing validator. The question is my question is more regarded towards, is it a constraint that we need to put on whatever the database implementation we come up with? Like, does it need to support synchronous or asynchronous API? Or is it something that we can work around? And if you say, for example, at the end of each block, we could also like try to do it on a file system level, like force flushes there. That's where my question.
I see. Yeah, I think
where my question comes from.
Yeah. So in that sense, then I think, it'd be possible to work around. Yeah. So that might suggest we may want to change something about the API, because right now the syncing is kind of part of the API. We have the like set and set sync.
Yep. Cool.
Yeah.
Was a great rundown. Thanks, Anton.
Cool. Yeah. So I guess we'll follow up in GitHub issues and so on. This was great. We'll discuss online who's going to go next, and I guess that's it. Thanks, everyone.
Thanks.
Yeah, it's very cool.
Thank
Thank you.
you.
Cool. Bye-bye.
Bye. Latest.
Everyone.